Hello everyone, this is Professor Robert Solis and welcome to this video lesson. So the first thing that I want to do is I want to go through some lecture notes that I have here, and then I'm going to record my computer screen, specifically using Visual Studio, to show you some of the different behavior of some of the different assembly code that I'm going to talk about. So in chapter 12, let's start off with the bit operations content. So over here, you'll see that we're going to talk about some of the various logical operators that are available in assembly language. And specifically, we'll talk about the AND. Now, it's important to note that we are talking about the Intel processor, right? So let me go ahead and write Intel, because that's going to be different than the Motorola processor, Motorola. It's going to be different based on the CPU that you are using. And in this particular case, if we're talking about the Intel processor, let me erase this. You'll notice over here that the syntax for the AND operator is destination and then source. So let's take a look at an example of that. So over here, in terms of code, you'll first notice that I've placed a hexadecimal value into into a move statement that's going to be moving that into the EAX register. So first, let's move this hexadecimal value into the EAX register. Then we're going to move this hexadecimal value into the EBX register. Now, the reason why I know that that's hexadecimal is because of that guy right there. The 0x prefix means that we're dealing with this as if it's, not as if, it is, in fact, it has a hexadecimal value. And then we have an AND statement. All right, so the AND statement is going to AND the EAX register with the EBX register, and hence the syntax destination source. All right, so at the end of this, the EAX register now contains 00001010. And so the question is why? Okay, well, the first thing, if we're going to understand what's going to happen from a bit level orientation or perspective, we're going to have to convert these hexadecimal numbers into binary. So the first thing that we'll do is we'll take the number that was placed into the EAX register and we'll rewrite it over here. But now let's go ahead and change that to binary. So the first thing that you'll notice is that F is converted, and that's placed over here. So F is nothing more than 15. 15 in binary is 0000. All right, then we're going to take E and we're going to do the same thing, right? That's 14. This is 13. This is 12. This is 11. This is 10. This is 9. And then finally, this is 8. All right, so we've just taken this entire hexadecimal number and we've converted that into a binary equivalent. All right, and then we're going to do the same thing for the number that was placed into the EBX register. So that's done over here. So let's take this, convert it into binary. Well, this 0 is a hexadecimal number, but now in binary it's 000. Same thing with all of these. This number right here is 1 in hex. Well, that's the same thing as 0001, and so forth and so on. All right, so now that we've taken these numbers and converted them into binary, so let's see here. Let's AND these two binary numbers together. Okay, so let's take this number, rewrite it over here. Let's take this number, rewrite it over here. And now let's AND them together. Okay, so if you're going to AND them, it doesn't matter if you're starting from left to right or from right to left. We're just simply working with the columns. So 0 and anything is 0 because that's the logical operator, and is always going to be false unless it's true and true. So for example, over here you see true and true, or 1 and 1, and so that's why the answer is 1. Any other case, the answer is always going to be 0, so it doesn't matter if it's 0, 1, if it's 0, 0, if it's 1, 0. You can see over here it's always going to be 0 unless both the inputs are true, and that's the only time that you're going to have a true value. Okay, so therefore I'm just simply going column by column, taking care of each one of these and writing them down. And so you'll see the only times that I have true are right here and also right here. And everything else, as you can see, is false. Okay, so now let's go ahead and take this binary number and convert it into hexadecimal. So if we were to convert this into hexadecimal, so that means that we're going to take this portion right here, and that's going to be 0. Let's take this portion right here, and that's going to be 0, so forth and so on. Now, if you take a look at this one right here, 0001 is the same thing as 1 in hexadecimal. 0001 is the same thing as 1 in hexadecimal. So that means at the end of our program, when you AND all of these, what is the value in the EAX register? It should be 0001010. Okay, so now I'm going to switch over to Visual Studio so that you can see this code right here and then see how I determine what actually is contained within the EAX register. Okay, hello everyone. We're over here now in Visual Studio. So the first thing that we're going to do is we're going to take a look at the logical AND operation. So let me just go ahead and put a comment over here and we'll say logical AND. Logical AND. And so what I've done is I've created an inline assembly program here within Visual Studio. And so what we just saw for the logical AND sample code was we're going to move into the EAX register 0xFEDCBA98. So that's a hexadecimal number that we're moving into EAX. Then we're going to move into the EBX register 0x00001111. That's another hexadecimal number. We are then going to apply the AND operator of the EAX to the EBX register, and let's find out what the contents are of the EAX register. So what I'm going to do is I'm going to place a break right here to stop the code in this this area over here, this grayish looking column. If I click over here, it stops the code. So let's go ahead and run it and see what happens. So it's building it. There were errors. No, I don't want to. All right, I find out what the error is. I said MOX. MOX. I keep on doing that. I meant move. Okay, we're going to move into the EAX register this number. All right, so I'm done here. So now let's go ahead and rebuild. And let's see, everything built successfully. Good. Okay, so now let's go ahead and run the code. All right, good. We are stopping the code over here. So I want to take a look at the contents of the EAX register. Now you'll notice over here that I have the registers panel. And the way that I did that was when you stop the program, if you were to go to Debug Windows, and then you go over here to, let's see, where is it? Registers. If you click on that, then you're going to get this. Now, it may very well be that registers is down here, right, like that, or it may be that registers is just floating on the screen like this. So typically what I do is I like this thing on the left hand or on the right hand side. So what I do is I take this, I hover on top of that semi-transparent area, and so you see what that looks like. Now because I've done that to several other panels, let me go ahead and reduce this. Because I've done that to several other panels like memory 1 and autos and locals, you'll see that I have a bunch of these. So you may have several of these tabs over here, or you may not. But in essence, for this exercise, all I need is the registers panel, so I can see what's in the EAX register, which is basically garbage, right? Who knows what could be inside of the EAX register? I just turned on my computer, or I just ran this program. We don't know what's inside there. But right now, I'm about to move this value. So I'm going to go ahead and click on Step Over. And so now you'll see that FEDCBA98 has been moved into the register. All right, now I'm about to move into the EBX register, which again is just garbage. I'm going to move into there 00001111. So I'm going to go ahead and click on Step Over, and so sure enough, that's been moved into the EBX register. And so now what I'm going to do is I'm going to perform an AND of those two registers. So when I perform an AND, you'll notice that now the EAX register contains the value 00001010, which is exactly what I said would be in this when you perform the AND of these two registers. Okay, so that is our Visual Studio perspective for logical AND. Okay, so we're back, and now we're going to talk about logical OR. All right, so for the logical OR operator, again, notice that for the Intel processor, right, So for the Intel processor, this is going to be different for the Motorola processor, say for example. But for the Intel processor, you'll notice that it says or and then destination, or rather destination and then source is what I meant to say. Erase that. All right, so here's some example code. Well, the first thing I'm going to do is I'm going to move a value into the EAX register. Then, for this statement, I'm going to move 00001111 into the EBX register, and then I'm going to apply the OR operator. All right, well, at the end of this program, you'll notice that the whole thing comes out to FEDCBB99, which is a little bit different than what I had over here. But the question is why? Why does that happen? All right, so let's go ahead and take this number and let's go ahead and convert that into binary. So using the similar fashion that we did with the previous example, F is 15, so that's 1111, E is 14, so that's 1110, and so forth and so on, right? We're converting all of these numbers to binary. So this is the binary representation of this hexadecimal number. All right, now let's take this hexadecimal number and we're going to convert that into binary, and that's going to be this over here. All right, so now let's OR these two binary numbers together. So if you're going to OR the two numbers together, here's the thing to remember about the OR operator. Anything that is going to be, if you have any input, I should say, that has a true input, then the output is true. So notice for this first column right here, I have a 0 or 1. Well, that's going to be a 1. Over here, I have a 1 or 0. That's going to be a 1. I have a 1 or 1. That's going to be a 1. So the only time that you're going to get a 0 or a false output is when both of the inputs are 0. So over here I have a 0, and then over here I have a 0. So 0 or 0 is 0. Okay. So you'll notice through the output, once I OR this row with this row, you'll see that this is what the value is. And so now our job is to take this, which I've just simply rewritten over here. We're going to take that and we're going to convert that into hexadecimal. Well, a bunch of ones, 4 ones specifically, that's F. And then this is the same thing as 14, which is hexadecimal E, and so forth and so on. Oops, let me undo that. And so forth and so on. All right, so you'll notice at the very end, when I turn that into hexadecimal, this is going to be FEDCBB99, which is exactly what I have over here, FEDCBB99. So in terms of the Y, well, we've just answered that question over here. All right, so what I'm going to do is I'm going to switch to Visual Studio so that you can see what it looks like from that perspective. Okay, so now we're going to take a look at the Visual Studio perspective for logical OR. So I will just simply replace that with OR. And we're doing something very similar. We're going to move a value into the EAX register, which is FEDCBA98. And then we're going to move into the EBX register 00001111. But instead of performing the AND operation, I'm going to perform the OR operation. So I'm going to perform the OR operation. And then the question is, well, what are you going to OR that with? Oh, by the way, I think I made a mistake in my notes because I think I just put this down, just the register, but I didn't indicate the source. So I do have to indicate the source. So we will, I'll take care of that later on. Let's see what happens now. So I'm going to run this code. Hopefully everything works fine. Here we go. So we're stopping the code. We are about to move into the EAX register this value. So let me go ahead and step over, and sure enough, there's FEDCBA98. We are about to move into the EBX register 00001111. And now we're about to perform an OR operation of the EAX to the EBX register, and you put the results right back into the EAX register. So when I do that, you'll see that the EAX register is FEDCBB99, which is exactly what I had on my lecture notes that you just saw when you apply the logical OR operation of these two registers. So that is it for this Visual Studio perspective. Let's go back to the notes. Okay, so now let's talk about logical OR. Logical OR is a very interesting operation. Once again, it operates by for the Intel processor destination source in terms of the exclusive OR. And let's take a look at the code so we can see how this works out. So the first thing that we'll notice is that we are moving a number into the EAX register. We're going to move another number into the EBX register. And then we're going to apply the exclusive OR of EAX to EBX. All right, if I take a look at the EAX register after we've executed the above code, I now find that the EAX register contains FEDCAB89. And of course, the question is why? Okay, well, the first thing that I want to do is I want to take the number that was originally placed into the EAX register, here it is, and let's go ahead and convert that to binary. So when I convert that to binary, F is 1111, E is 1110, so forth and so on. Let's go ahead and take the number that was placed into the EBX register, that's this guy over here, and let's go ahead and convert that into binary. So that 0 is 0, 0, 0, this 0, 0, 0, 0, 0, this 0, 0, 0, 0, 0, so forth and so on, right? So we have these numbers. We've converted this into binary. Now let's exclusive OR these two binary numbers together. So the goal or the way you should think about this is as follows. Anytime that you see a difference in the two inputs, if there's a different input, like if one of the inputs is 0 and if one of the inputs is 1, then the output is going to be 1. So in other words, 0 exclusive OR 1 is 1. Put another way, 1 exclusive OR 0 is 1. So notice that these are different, right? This is a 0, this is a 1. I'm sorry, this is a 1. So they're different. So therefore, since they're different, the output's going to be 1. It's only when the inputs are the same that the output is false. So notice over here I have a 0, then I have a 0, so the output is false. Once again, let's see if we can find a 1, 1. Here it is. So the input are the same, so notice what ends up happening. The output is false. So anytime that the inputs are the same, the output is going to be false. So we take that for every single column and we figure that out. Anytime that there's a difference, the output is 1. Anytime that there is a similarity, the output is going to be 0. All right, so now I take this result and I'm going to convert that now from a binary number into a hexadecimal number. Well, as you can see here, for ones is F. Over here, I have 1100, which is, let me see here, so it's 10, 11, 12. So that should be 12. 9, or 1001, that's binary. And so that's going to be the 1's position, the 2's position, the 4, the 8 position. 8 plus 1 is 9, so that's why we come up with 9. Anyway, by the time we convert this whole thing, it's going to be FEDC AB89. And as you can see over here, that's exactly what we got over here in terms of our output for the EAX register. That's why this is the answer, because when you exclusive OR each of these different bits, you are going to get a 1 at the output if there's two different inputs, or a 0 at the output if they're both the same. All right, so what I'm going to do is I'm going to switch over to Visual Studio, and then in Visual Studio, we'll see what this looks like from running this code from that perspective. Okay, so now what we're going to do is we're going to work with exclusive OR. And so according to the notes, it was supposed to be move EAX move into the EAX register, FEDCBA98. Okay, so that's what we've done over here. We're going to move into the EBX register, 00001111. Okay, good, we've done that. But instead of this, what we're going to do is we're going to use the exclusive OR operator, which is XOR. We are going to apply the exclusive OR operator of the EAX register and to the EBX register. So we're exclusive ORing these two registers, but the way that this guy works out is it puts the answer right back into the EAX register. So we'll stop the code over here to see how this thing works. All right, so the first thing that we're going to do is we're going to move this value into the EAX register. So I will step over, and so now notice FEDCBA98, which is this value over here, has been moved into the EAX register. Let's move this into the EBX register. So you can see that that has happened. And now we are going to perform the exclusive OR of these two registers and place the answer right back into the EAX register, which is currently this. But when I step over, now you'll see that the exclusive OR of these two numbers is FEDCAB89, which is, again, exactly what I said would happen based on the notes that we just took a look at. Okay, so this is your Visual Studio perspective. Okay, so we're back, and now let's talk about logical and. Okay, so not logical and, sorry, logical not. All right, so the not logical operator basically is an operation that flips. So here's what the syntax looks like. As you can see here, it's simply going to take a register, or it's going to take a value located in memory. And what does it say it's going to do? It's going to logically negate, right? Logically negates the content. So in other words, it flips all of the bit patterns. Okay, so let's take a look at example code. Let's say that I get this hexadecimal value, and I'm going to move this into the EAX register. Then I just simply say not EAX. So what that does is it flips all of the values. That's what it means to apply the not operator. Well, at the very end of this code, I look at the EAX register, and now the EAX register contains this. And so the question is why? Well, let's go ahead and investigate that and see if we can find out why that's the case. All right, so the first thing I'm going to do is I'm going to take the number that I placed into the EAX register, which is this hexadecimal number rewritten, and I'm going to convert it into binary. All right, so F is nothing but 1111, 8 is 1000, and so forth and so on in between. Now that you've converted this into a binary number, what we're going to do is we're going to not the contents of the EAX register. All right, so to not the contents, and all I did was I just took this, I rewrote it over here, and then now this right here is the flip of all of the bits. So that 1111 becomes 0000. The 1110 is 0001, and so forth and so on. So you're going to take each of these different values and flip them. So this last one over here is 1000, therefore flipped, it's 0111. All right, so now that I have the binary value after the not operation, let's go ahead and take that binary number and convert it into a hexadecimal number. So I'm going to take this and I'm going to rewrite it over here. Well, a bunch of zeros is nothing more than hexadecimal 0. 0001 is hexadecimal 1. 0111 is nothing more than hexadecimal 7. So you can see over here the answer should be 01234567, which is exactly what I said would be located inside the EAX register. And so you've demonstrated why that's the case, because this is how the not operation works. So now let's switch over to Visual Studio and see what it looks like from that perspective. Okay, so we're back over here in Visual Studio, but now we are going to be talking about not. Oh, I forgot to put exclusive for on my previous example. Okay, so sorry about that. But now we're going to be talking about logical not. Well, let's see. I'm going to go ahead and erase all this code that we were previously working on, and we're going to type in move into the EAX register, the hexadecimal number FEDCBA98, and then we're going to perform a not of that particular register. And what's going to happen? All right, so first of all, I'm going to stop the code over here at the move statement. So let's go ahead and run this. And then now that we've stopped the code here, I'm going to step over. And so you'll notice that FEDCBA98 has been moved into the EAX register. Now let's perform the not, which you know is simply the flipping of all of the different values. So if I were to step over that, notice what happens to the EAX register. It's 01234567, which is exactly what we talked about in the notes would happen when you use the not operation for this particular value. All right, so let's head back to the notes. Okay, so we're back, and now what I'm going to do, let me switch this to page width. Let's talk about the neg operation. So let me switch over here to lasso. All right, here we go. So in terms of the syntax, this is what it looks like. Basically, it performs a two's complement negation. right? So whatever the register is that you're looking at, EAX, EBX, blah, 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 you're going to get a two's complement. So let's say that in terms of the example code, that I move into the EAX register FEDCBA98, and then I apply the neg operation to that. What's going to happen? Well, first of all, I'm saying that the EAX register now contains 0, 1, 2, 3, 4, 5, 6, 8. And the question is why? All right, well, first of all, in order to be able to dissect that, let's take the number that we moved into the EAX register. So here it is, and now we're going to convert that into binary. So if I'm going to convert that into binary, F is 1111, E is going to be 1110, so forth and so on. 8 is going to be 1000. Once I've converted that into binary, now I'm going to perform the ones complement. And the ones complement, as you'll recall, is nothing more than flipping the bits. So the 1 becomes a 0, the 1 becomes a 0, 1, 0, 1, 0. The 0 becomes a 1. So this is 1 to 0, 1 to 0, 0 to 1, 1 to 0, so forth and so on. So basically what we're doing is for every single one of these bits, we are flipping them over so that it becomes the opposite, or the flip, right? Ones become zero, zeros become 1. Once I've done that, now let's go ahead and perform the twos complement. And the twos complement is nothing more than adding 1 to the ones complement. Okay, so let's go ahead and get started on this row over here. So you see over here that 1 plus 1, well, that's going to be 1, 0 in binary. So I put the 0 over here, and then I put the 1 over here in the next column to carry. Well, now I'm going to have 1 plus 1. Well, that's 1, 0, so I put the 0 over here, and I carry the 1. So that's going to be 1 plus, or yeah, that's right, 1 plus 1. That's going to be 0, and I carry the 1. 1 plus 0 is 1, so I put the 1, but there is no carry. And so that means now I'm just simply putting down the rest of the values here. All right, so now I know that this is the two's complement. So let's convert the binary number into hexadecimal. All right, so I'm going to take this number and I'm going to rewrite it over here. So if I'm going to convert that into hexadecimal, you'll see that 4 zeros, that's nothing more than 0. 0, 0, 0, 1, that's going to be hexadecimal 1, and so forth and so on. 0, 1, 0, 1, that's 5. 0, 1, 1, 0 is 6. And then finally, 1, oops, let me undo that. 1000 is hexadecimal 8. So the answer is 0, 1, 2, 3, 4, 5, 6, 8, which is exactly what I said is inside of the register. So now you know why that happened, because the negation is nothing more than the two's complement. So now let's take a look at this code from the perspective of Visual Studio and see what it looks like over there. Okay, so now we're going to talk about logical neg, which basically you just learned performs a two's complement of the code, or a two's complement of the number that we're interested in. So in this case, what I'm going to do is I'm going to take the number FEDCBA98, I'm going to move that into the EAX register, and then I'm going to change this to neg, which basically performs a two's complement on the EAX register. Okay, let's go ahead and run the code, and I'm going to move into the EAX register by stepping over FEDCBA98, perfect. And now let's go ahead and perform the two's complement. So if I were to step over, it says that the answer is 0, 1, 2, 3, 4, 5, 6, 8. And you saw the explanation back in the notes that that is, in fact, the two's complement of hexadecimal FEDCBA98. Okay, so let's head back to the notes. Okay, we're back. So let me go over here to page width. And now let's talk about shifting bits. Okay, so let me select the lasso. We're going to talk about shifting bits. All right, well, first of all, the mnemonic, the assembly language mnemonic, is SHL, which basically means that we're going to be shifting bits to the left, and I'll describe what that means. In terms of the syntax, what you're doing is you're just simply going to be using SHL. You're going to indicate what register it is that you want to shift, And then you're going to give the amount of the shift, which I'm saying in this particular syntax is going to be an 8-bit constant. All right, we'll take a look at that in just a moment. All right, so over here, notice for my example code, notice that I have the move operation, and I'm going to be moving something into the EAX register. Well, in this case, I'm going to be moving this number, which is a hexadecimal number, 00000001. All right. So now that I have this number in the EAX register, let's go ahead and apply this shift to the left of the EAX register by how much? By 1. So we're going to shift once to the left. So if I shift once to the left, I'm saying that at the end of this, the register rather, now contains the number 1. If I were to shift to the left again one time, the register now contains 2. If I were to shift to the left by 1, the register now contains 4. And I think you can see a pattern over here, 1, 2, 4. So basically what we're doing is we're multiplying times 2. 1 times 2 is 2. 2 times 2 is 4. If I were to do this again, 2 times 4 would be 8, right? So this is nothing more. What happens is basically shifting to the left is nothing more than multiplying. It's a multiplying factor. So the effect of shift left is to double the contents of the register. So let me just go ahead and write a quick note over here just so I can show you what it looks like. So let's say, for example, if I have 0, 0, 0, 0, 0, 0, 0, 1. Okay, so if I were to take a look at this, this item, that's in the ones position. If I take that and if I shift it to the left, that's going to push this 0 out. This 0 comes over here, and so forth and so on. And then that 1 comes over here, and then we just insert another 0. Well, this is the ones position. This is the twos position. So now the shifting has caused this to be 2, and so forth and so on. Right, so let me go ahead and erase all this stuff so that my notes can be neat. But that's basically what's happening when we're shifting. Now, you know what? I think I may have an error in my notes over here because it says that okay, I'm originally putting in 00000001, but then when I shift it to the left, it says that it should be that the register now contains 1. I think that may be a typo. I think maybe that should be 2, and this should be 4, and this should be 8. So I'll tell you what, let's switch over to Visual Studio and verify what's going on, and then I can come back and take care of my notes. Okay, so we're back. So here we are going to be talking about the mnemonic. Now, I don't want to say that this is a logical operator. This is something that operates on bits. And so we call this shift left. SHL is the shift left assembly language mnemonic. So let me go ahead and retype or I shouldn't say retype, just type the code that was that were located on our notes. Inside of the EAX register, I'm going to have the hexadecimal number 00000001. And then I'm going to perform a bunch of shift lefts to the EAX register by 1. And it looks like I have 3 of these on the notes. So I'll take this guy. I'm going to copy and paste it like that. So I have 3 of them. And let's observe the behavior of what happens inside of the EAX register. Okay, so I'm going to go ahead and run the code. Here we go. I'm about to move the number 1 in hexadecimal into the EAX register. So I step over, and here it is. 1 is now inside of the EAX register. And we are about to take that, and but we have to think about this from a binary perspective, and we're going to basically shift to the left by 1. So when I do that, you'll notice now that 1 becomes 2, because basically we're just doubling. 1 goes to 2, 2 is going to go to 4, 4 is going to go to 8. In fact, that's what's going to happen over here. Now you see that EAX register has 4. We're about to do that again. If I double that, now it becomes 8. So one of the things that you have observed, is that shift left is like doubling, right? Or multiplying times 2, whatever the value is inside of the EAX register. Okay, so let's head back to the notes. Okay, so we're back and we just discovered that my notes are wrong. So let's go ahead and erase this. This is supposed to be 2, that's supposed to be 4, that's supposed to be 8. So let me go ahead and write those values down. The register now contains 2, the register now contains 4, and the register now contains 8. Boy, am I glad I caught that. Okay, so basically the process is that the shift left register is going to be multiplying values as they switch bit patterns from right to left. All right, so now let's take a look at shifting right. So the assembly language mnemonic is SHR, which means basically shift to the right. And you'll see that the syntax is that you indicate what it is, what register it is that you want to shift, and then you're going to give an amount by how much it's going to shift. And in this case, I'm just simply representing it as a 8-bit constant. All right, so let's take a look at the example code. And over here in this statement, you'll see that I am moving into the EAX register the number 000000008. So now what we're going to do is we're going to take that number and we're going to shift it to the right. And what I'm saying is when you shift this to the right by 1, the register now contains 4. And if you do the same statement again, the register now contains 2. And if you were to do this again, the register now contains 1. So in other words, what I'm suggesting to you is that when you implement the shift right, that is in essence halving, right? The effect of the shift right is to halve the contents of the register. So in other words, you're cutting it in half. So from 8, it went to 4, and then from 4 to 2, and then from 2 to 1. So let's take a look at Visual Studio so we can understand this chunk of code from the Visual Studio perspective. Okay, so we're back over here and we're going to talk about the shift right mnemonic. So over here, I'm going to type in SHR, and I think what I'll do is I'll just simply copy this and paste and paste. So the first thing that we're doing is I'm going to move 8 into the EAX register. Once I've done that, then we're going to shift to the right the EAX register contents by 1, and we're going to observe to see what happens. All right, so first of all, let's go ahead and run the code. Sorry, let me just click on that, run the code. And the first thing that we should do is to move this into the EAX register. So I'm going to go ahead and step over and notice that 8 has been placed into the EAX register. And now we're going to shift right the EAX register by 1 amount. All right, so you'll notice that that 8 now becomes a 4. The 4 now becomes a 2. The 2 now becomes a 1. So once again, this is verification that shift right is halving, or divide by 2, divide by 2, divide by 2, over and over and over again. Okay, so let's head back to the notes. Okay, so we're back, and now we are going to move on to multiplication. All right, so for multiplication, you use the imul assembly mnemonic. And the way that it works out is that you're going to have the register that is going to be, the one number that you're going to multiply times another particular number. Another way that you could use this is you can say, okay, a particular register, like EAX, say, for example, times 2, right? That would be some sort of a memory location that contains a number. So in terms of an example code, notice the following. So first I'm going to move into the EAX register the hexadecimal number 000000002. Okay, so I move 2 into there, and then I'm going to use the imul of the EAX register, which is the number 2 in hex, times 10. All right, what would that be? And so what I'm saying to you is that the EAX register now contains 000000014. Why? Well, first of all, it's important to remember that this is not a decimal number. This is a hexadecimal number, right? So you think 2 times 10, that's 20. Why is it coming up as 14? This is being represented as a hexadecimal number. So let's first of all take a look at this. So first, the goal of the above code is to multiply 2 times 10. That's really what we're trying to do. So second, 0x00000014 is what in decimal? So let's go ahead and take this number, and first, in order for me to convert it into decimal, I think early in the semester I showed you that to go to decimal, first take a hexadecimal number, convert it into binary, and then go ahead and take it from binary and convert it into decimal. All right, so here's my hexadecimal number. I'm going to convert this into binary. So that 0 is really 0000. This 0 is 0000, and so forth and so on. That 1 is 0001. That 4 is 0100, right? Because this is the 1's position, this is the 2's position, this is the 4's position. All right, so now let's go ahead and add those bits. So if you take a look over here, you'll see this is the 1's position, 2's position, 4's position, 8 position, 16 position. So it looks like the 16-bit is on. It looks like the 4-bit is on. Well, 16 plus 4, that's equal to 20. So 00000014 in hex is really the same thing as 20 in decimal. So therefore, what the imul is, it's a multiplication operation. It's a multiplication mnemonic of the register times another register or a number. All right, and then I think this is our final topic. But before I do that, let's go to Visual Studio so that we can see this chunk of code in action. Okay, so we're back over here. Now we're going to talk about how to multiply, and so we use the imul, right? We use the imul assembly language mnemonic. And so let's go ahead and get rid of this code. Let me type in some new code. So the first thing that I'm going to do is I'm going to move into the EAX register 0x00000002. So I'm moving hexadecimal 2 into the EAX register. And now, according to the notes, I'm going to apply imul to the EAX register. Basically, I'm going to multiply it times 10. All right, so let's see what happens when I run this code. The first thing I'm going to do is I'm going to move 2 into the EAX register. So I'm going to step over, and there's the number 2. Now what I'm going to do is I'm going to apply that 2 that's in the EAX register. I'm going to multiply times 10 and put the answer right back into the EAX register. So when I step over, you see, first of all, it's 2. When I step over, well, what is 2 times 10? Well, 2 times 10 is 20 in decimal, and 14 is the hexadecimal representation of 20 in decimal, which is exactly what we talked about in the notes. So now, speaking of the notes, let's head back to the notes. Okay, so I'm back. Now let's go ahead and discuss our final topic, which is going to be division. So division, you use IDiv, and you can perform that division to a register or to a memory amount, which is a number that's contained in memory. So let's take a look at that to see what it looks like in code. So the first thing that I'm going to do is I'm going to move into the EAX register a number. And so in this case, it's hexadecimal A, which is the same thing as decimal 10. So I'm moving 10 into the EAX register. And then I'm going to move 3 into the EBX register via the move mnemonic. And then I'm going to perform an IDiv. Now notice that IDiv has just, this one register. Well, what this is doing is it's basically saying, what is EAX divided by EBX? That's what's happening. It would be the same thing as me saying, okay, let me write this down here. What's 10 divided by 3, right? That's in essence what's happening over here. What is the number inside of the EAX register divided by the number in the EBX register? Okay, so now let me undo all this stuff. All right, so now, and in fact, let's take a look at this description over here. It says, divides the contents of the EAX register by the EBX register and places the quotient in EAX and the remainder in EBX. So I guess if I were to just do a quick, let me just go ahead and write some stuff down over here. Let's say over here that this represents the EAX register, and this represents the EDX register. And in EAX, currently I have the number 10. Now I'm going to take that 10, and I don't have the EBX register, so let me go ahead and put that down. EBX register, I have 3. I'm asking what is 10 divided by 3? Well, you know that that's 3 with a remainder of 1. So what would happen is this EDX register would not be replaced with the number 3, and inside of the EDX register, there would be a number 1 here, because EDX register holds the remainder, EAX register holds the quotient, which is that number right there. Okay, now let me erase all this stuff and delete. Oops, I forgot to delete that, so I'll just simply do this. Good. Okay, so the above does, but okay, but here's what I'm saying. You may think, okay, let's go to Visual Studio and let's, go ahead and perform this. But boy, I had to learn this the hard way. This code does not work. The code doesn't work because this is what must happen first for Intel processors. So let's read this. The above does not work because we must first clear the EDX register. So consider the following code, or the code fragment. So it looks like I'm pretty much duplicating everything. There's that move statement, there's the move statement, but look at this guy over here. That exclusive OR operation, notice what I'm doing. I'm basically saying exclusive OR EDX with EDX. And then that IDIV operation I perform. All right, so here's what has to happen. In order for you to store, or in order for IDIV to store the remainder into the EDX register, which is what we saw happens over here, right? Or over here, I should say. In order to do that, we have to make sure that the exclusive OR, we need to make sure that the EDX register is cleared. And the only way that you're going to be able to do that is to exclusive OR that. And so that's a technique. If you want to clear something, you just EDX it with itself. So let's see what happens. Let me just go ahead and write down. Let's pretend that inside of the EDX register, let's say that I have 1011, say for example. All right, well, if I'm going to perform an exclusive OR with that, it says over here that the EDX register is supposed to be applied, or an exclusive OR with the EDX register itself. Okay, so let me go ahead and write down another one of these values. So 1011, and let's go ahead and apply an exclusive OR. Well, remember that for exclusive OR, and I'll go ahead and write down the truth table for exclusive OR. So X exclusive OR Y, I have 0, 0, 0, 1, 1, 0, 1, 1. Anytime that the values are the inputs are the same, the output is going to be 0. Anytime where the inputs are different, the output is going to be true. So notice over here that for 0, 0 as the input, the output is 0. For 1, 1 as the input, the output is 0. So then what would happen is, since these are two of the same, 0. Since both of these are the same, 0. So that's one way of thinking about this. Whenever the inputs are the same, the output is going to be 0. So now I think you can see that what the exclusive OR operation does is it serves as a clear operation by exclusive ORing it to itself. And so that's what this thing is going to do over here. It's going to provide an exclusive OR of the EDX register. Therefore, the EDX register is going to be clear. Now you can perform an IDIV. And so when you perform an IDIV, it's going to store into the EAX register the quotient, and it's going to store, if there is a remainder, into the EDX register. So that's why I mentioned over here, the result of the above code is to place 3 into the EAX register and 1 into the EAX register. So now let's switch over to Visual Studio and see what that looks like from its perspective. Okay, so our final discussion then is working with IDIV. IDIV meaning that you are working with integer division, right? So we're going to be dealing with a bunch of integers. So what are we going to do? Well, the first thing that I'm going to do is I'm going to move into the EAX register the number 10, which in hexadecimal is A. And I'm going to move into the, EBX register 0x1234 1233, the hexadecimal number 3. Basically what I'm doing is I'm simply saying, what is 10 divided by 3? Now, this is a mistake, as we spoke about in the notes. I shouldn't do this step first, right? What I should do is first clear the contents of the EDX register. And the way that you do that is with exclusive OR. When you exclusive OR EDX with EDX, what you're doing is you're clearing the contents of the EDX register. Then you can go ahead and perform your division. See, what happens is the remainder is placed into EDX, the quotient is placed into the EAX register. So that's why you have to do this. This is just something you've got to do in assembly language when you're dealing with the Intel processor. Maybe it's different for the Motorola processor, but for Intel, this is something that we have to do. So let's go ahead and step through this by first running it. And the first thing I'm going to do is I'm going to move A into the EAX register. So there's A, which is 10. I'm going to move 3 into the EBX register, and sure enough, there it is. All right, now it just happens to be that the EDX register contains this, right? Your screen may have something different. But after I perform an exclusive OR of EDX to EDX, it should clear this whole thing out. So sure enough, when I do that, notice now that the EDX register has been cleared out. Now I can perform the integer division of the EAX register divided by EBX. But notice that you just write EBX, which is what is it that you want to divide EAX by? So if I were to translate this into English, divide the EAX register by whatever is inside of the EBX register. Translation, divide 10 divided by 3. And put the answer right back into the EAX register and the remainder in the EDX register. So let's see what happens when I step over. So I step over, well, you know that 10 divided by 3 is 3, and so that's why you see in the EAX register, there's the 3. Now the remainder is 1, and so that's what the EDX register holds. It holds the number 1. That's why we had to clear the EDX register, because had we not cleared it, it would have maybe put an erroneous value in here. So you got to clear it first so that it can contain the remainder. The EAX register then contains the quotient. And that is it. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.